think I finally got it started. Had trouble with the stream there. Let me go in here and see. Is that good time? Anyway, go to the next one. Right, the next one. No, the next one. Okay, I think I did that one already. Although I did not finish it out. Okay. I guess I left it unfinished there. Okay, so what I did is I inserted this in here, up, and took this over here. Because apparently I did not. Okay, so there's your V1. The V1, replacing the V1 here with the V1 here. Gives me this. And then row we squared over 2. Then I get 0.2 times gamma, which I'll know gamma because it's going to be water, equals to rho z squared, 2 squared over 2 times 1. And then I'm going to bring this over here to be d. Okay, so one of the things that I have to be mindful of is that I said that, but in fact, you're squaring a square, so this should be that. To the 4th. Now, if you want V2, you end up with this. Okay, so what you want to do, first thing you want to do is bring your 2 up there. 0.2 times gamma times 2 divided by taking all this and putting in the denominator over here. 1 minus d over 0.1 to the 4th. And then, of course, you got to bring, you brought your 2 over, but you didn't bring your density over. So that's how v is a function of d, because we actually put in 1.94 here for the density, and you put in 62.4 here. Okay, so let's look at, okay, so we did that one. you get this one, that one, now this one. So he wants you to do the same thing here. He wants you to determine the flow rate as a function of diameter. Now, of course, if you wanted to, this is a velocity as a function of diameter, and then all you do is you multiply it times the area, which, guess what, the area at 2 has the d in it, and that would be q, area 2. The area 2 would be pi d squared over 4. So this, in fact, would be your answer. In fact, q can be written as a function of the d. In this particular case, we'll start off and do the same thing. We ended up starting with the point here. I'll change to a brighter red here. So we end up with a point here. And we end up with a stagnation point here. So we go from 1 to state 2. So again, P1 plus gamma V1 plus rho V1 squared over 2 is equal to P2 plus gamma V2 plus rho V2 squared over 2. Elevation is the same. So these equal and therefore can be canceled out. P1 can be replaced by this value of k. So what I'll do is it will be an unknown value of k times gamma v1 squared over 2 is equal to, now here's your p, this is stagnation. So the v2 is equal to 0, meaning a particle will stagnate right here. One that comes next to it might go up and around. One that comes next to it might go up and around. But this whole face is stagnant. Otherwise, if it had a velocity with it, this would have a velocity, and it would flow out the top. Now, in fact, if this is too short, the water can flow out the top if the manometer tube is not tall enough. And then you won't get stagnation, you'll just get leaking onto the floor. But for this particular case, we've drawn it as though it's stagnating on the top. If you want to write P2, you would just basically say 0.2 plus the K times the gamma. That's the pressure that you take in order to go down to that 0.2. Now, there is only V1. Okay, so this can cancel out. Rho V1 squared over 2 is equal to, now take this out, and that'll take this out. You'll get 0.2 gamma. And then you could say V1 is equal to the square root of 0.2 times gamma, another 2, over rho. Now, the only way that this is a function, okay, it's not a function of d. You can't write. Okay, so if you do A1, you get 0.1, that's the diameter there, 0.1 squared over 4 times pi times V1 is equal to Q, which is equal to pi, 0.1 squared over 4, 0.2, 62.4, so that's gamma, and 2 over 1.94. There is no D over here, no diameter. So in fact, it really does not matter what the diameter is over here. you're not going to be able to write the flow rate as a function. Now, you can find the flow rate if you've got this, because this is your elevation that's up here. You can find that, but you cannot. There's nothing here that makes the D dependent. Okay, so let's work this problem. Water exits a pipe as a free jet, flows to a height above the exit plane. The flow rate is steady, incompressible, frictionless. There mean no losses. The only way you have losses is through that not equaling here. Determine the height. Determine the velocity and pressure at section 1. It's 6 inches in diameter. So he's already labeled 1. So you can just take off and label. If you don't know what to do, you can't use 1 because there 1's already used 2 and then 3. So here's what I'm going to do. I'm just going to randomly label a bunch of locations. And then what I'm going to do, before I go anywhere, I'm going to look at location 1, and location 2, and location 3. Pressure, elevation, and velocity there. And I'm going to see if I know these. Now, at top, at 3, this is equal to 0. Pressure there is equal to 0. Height is equal to h. Okay, so at this particular point, right here, which I'll label it, I did label it 2. At 2, velocity is 16. Okay, now, I have to go back and look at this because I didn't identify my datum yet. So I think I want to identify my datum as my lowest point. So if I did that, then the height here would be h plus 8. So I was remiss in doing that. So now let me do this. This would be 8 and location 1. So I know the heights here. It's told me the velocity here. The thing is, when it moves outside of this realm, meaning that this is atmosphere, if in fact, so if in fact this were, so what you have here is pressure is equal to 0 here, in here, in here, in here, in here, in here, and all the way up. So you have the same thing here. So the pressure is 0 all the way up here. The question is, what's the pressure in here? Well, if the pressure was higher, and you can see this if you take a soap bottle and you pressure it very, very hard, you know, where this is liquid soap, you'll see what's called dye swell. It'll come out like this. What's happening here is you have a high pressure here. And because you have a high pressure, it's pushing, okay, so you have to realize all along the edge, all along this edge, and all along that edge, pressure is equal to 0. The fact of the matter is you have a high pressure making the particles turn. If you want to look at dye swell, okay. Yes, yes. Boy, that is a very tiny That's really weird. Okay, so let me see if I can find a better. I don't know what I'm looking at here. Oh, that's somebody wanting. Let's just see what this looks like.
What if you could get rid of your kitchen garbage at the push of a button? Hey, I'm Matt.
Get rid of that. So in other words, it'll swell as it comes out of here. Maybe I'll make a video and add it at a certain point. So the fact of the matter that these are going straight up and not turning out like this or turning in means that the pressure is maintaining itself across the section. Meaning if you plotted the pressure, it would be a 0 all the way across to 0. If it did up and goes down, then the pressure in the center would push the particles out, and that would create a dipole. And usually it doesn't happen on fountains that go up. It usually happens the reverse. So therefore, this is the case. Whoops. Okay, what's going on here? Okay, so this is the case, and the pressure at the top is the case. Now, I'm sorry, pressure down here, we don't know. So we're going to label that P1. We don't know V1. So now, if you look across here, what row do you have if you know everything? This one you don't do. This one, you don't know everything, and this one, you don't know everything. So you have to use this one as the base. So if I write, I have one unknown here. So if I write between 2 and 3, P2 is gamma, V2, because V2 squared over 2 is equal to P3 plus gamma Z3 plus rho Z3 squared over 2. Now, well, here, that's a 0. And this is a 0. So what I get on the right hand side is gamma is 8 plus 8. That's from 3, row 3 here. From row 2, I get this being 0. I get this being 8. Gamma comes 8. And then I get 16 for the velocity. Rho 16 squared over 2. Now, I get 62.4 because it is water. Okay. Times 8 feet. So 1.94 slugs, cubic foot, times 16 squared over 2 equals to 62.4 times 8 plus 8. And it turns out this will cancel that. And then what you'll get is 8 will be 1.94. 16 squared divided by 2 is 62.4. And what you end up with is 1.94 times 16 squared divided by 2 divided by 62.4. H of 3.97 feet is equal to about 8. Now, how do you deal with the between 1 and 2? Okay, so here's what I mean. Okay, let me get rid of the die swell. Okay, So now I'm going to write between 1 and 2. And in here, I'm going to try to diagnose what the pressure and what the velocity is. So I'll just write them. V1 plus gamma Z1 plus rho V1 squared over 2 is equal to, and I'm just going to go straight for 2. V2 squared over 2. So all I do is take the values over here and I never figured out what these values actually were, but what I ended up with is 0 plus, so again I'm plucking them straight off here, and pluck this one straight off here and put in here. Okay, 62.4, that's gamma. Z2 is 8 plus 1.94, and the velocity 2 is 16 over 2. So my number becomes 62.4 times 8, that's 1.94 times 16 squared over 2, or 747.52. Now, P1. Okay, so here I'm grabbing this. I'm grabbing this right here. Plus 62.4 times 0, because that is this. And then I'm just grabbing this. Now, question is, what is B1? Well, if you look at this thing real close, and you remember some stuff from thermo, A1, B1 is equal to A2, V2. Now you can put density in front of it, but density remains the same on both sides. So what I'll get is pi diameter, I'm just going to use 4 inches squared over 4, times B1 is equal to, this is 6 inches diameter, 6 squared over 4, V2. If I want to, I can cancel this and this, and this, and then I can say B1 equal to 6 over 4 squared times B2, moving the 6 over here and taking the 4 under. Then I can basically say it's 3/2 squared, or 9/4 V2. Now, he told us what V2 was, and it was 16. So it's good as 9 times over 4 times 16, or 4 times 4, because that's 16. And so you get 36, or 9 times 4 is 36. So it's moving a little faster here than it is there. So you can say P1 plus 1.94 times 36 squared over 2 is equal to 747.52. The pressure at 2 is equal to that minus 1.94 times 36 squared over 2 equal to minus 709 and some digits. 26 pounds per square foot, or 3.58 psi vacuum. So P2 is equal to minus this. So it's a little bit of a vacuum there. Now, does that make sense? Well, yeah. Here, let's take a case in point where you have, and I'll do this and I'll move on and call it quits for today. Hang on, let me take the help of the screen. Okay, so the fact of the matter is, let's say you had a garden hose. Let's say this is, usually it's 3/4 of an inch diameter. And let's say we were producing, maybe 1 cubic feet per minute. Or maybe, let's just draw them down to maybe 0.01 cubic feet per second. Say it's not moving very fast. So let's say we drew it down to a diameter that was, say, I don't know, 0.1 inches. And then it came back up and it spewed out. But in the process, what we did with this small diameter, we put a hose down here. And in that hose, we put some soap, some sort of chemicals, and made it so that the atmosphere on the top, this was gauge pressure is equal to 0, so it's atmospheric pressure. Question might be, how high would this have to be? What would the height? First of all, let's find out what the pressure is here. Find out what the pressure is here at location 2. So what we'll do is we'll locate this as 0.1. We'll locate this one as 0.2. And we'll locate this one as 0.3. And we'll say this is 3/4 as well. Now we just write the Euler's equation between them. V1 plus gamma V1 plus rho V1 squared over 2. Well, before we do that, let's list our things. So we have our location, 1, 2, and 3. We have the pressure, elevation, and velocity. The datum is going to be such that it's 0 on all of these. As it turns out, we'll have the diameters, so I can find the velocity at 1, at 2, and at 3. And let me do that real quick. So let's say we had Q equal to, let's make it 0.1 instead of 0.01. So let's make it 0.1 cubic feet per second is equal to the area times the velocity. Now the area, we've got two different areas. There's the area of the hose, which will be both 1 and 3, which is pi 0.75 over 12. That's how many feet it is, over 4. So, let's see, pi times 0.75 over 12 squared over 4, 0.003, 0.003, 068. The area of the small section, which is actually 2, so 0.1 inches, 0.1 over 12 squared over 4. This time way down. 0.00005. Yes. 54542. Now, what is the velocity at 1 n of 3? It's basically Q divided by A1 or 0.1 divided by 0.003068 or let's see. That one. $32 feet per second. Let's look at the velocity at 2.1 over the small value, which we may end up with something that's unreasonable there. That's the small value. 0.1 divided by. Yeah, we knew that was something completely unreasonable here. That's way too high. So what I'm going to do is I'm going to adjust this and make it 0.2. Actually, I probably need to make it 0.25. So let's go back and say that that's not even possible. 0.25. You're going to have all sorts of problems here. If you have it too small, it's going to require so much pressure back here at 1 that you won't be able to sustain a flow rate of 0.1. So this is 0.25. Okay. What? I am so sorry. That's still too high. So it's 293 feet per second. This is going to require a huge amount of pressure to get this to come out. So you're not going to get this kind of pressure in the back, but it's okay. Let's just stick with this and say this is 0.25. And so we adjusted this so that the velocity there is 293. So let's find out what is the pressure at 2. Okay, this is completely unrealistic, but 2 plus gamma, C2 plus rho, P2 squared over 2. First of all, elevations are the same. Now what we have to realize is we can also write P3 plus C3 plus V3 squared over 2. Here's the thing. If we look at the exit, we know the velocity here. We know the pressure there. We don't know the pressure here. And we don't know the pressure here. I'm sorry again. It goes backwards. We do know the pressure at the exit is 3. We don't know the pressure here at 1. We know the velocity at 1 is 32. We're just going to say it's 32. This is 32. And this is 290. We'll just call it 290 roughly. Now, at this point, I know everything here, so I can find this pressure, P1. And we're going to end up with something interesting out of here. So we're going to work between 3 and 2. I don't care about 1. We're working between 3 and 2. Pressure 0. P2 is equal to 62 plus 1.94. Velocity 2 of 290 squared over 2 equal to 1.94 times, I think it was 32 squared over 2. So you get P2 equaling to something that is completely unrealistic, but it's a negative number, and that's the point I wanted to make. 32 squared minus 290 squared. I'm going to figure out the number, but it is going to be completely unrealistic because it's not going to be possible to do this. But my point is, 32 squared minus 290 squared is a large number, minus 83,000. That's way unbelievable, times 1.94 over 2 gives you minus about 80,000. About 80,000 pounds per foot squared. This is completely, again, outside of reality. Or minus 559 is, the point is, it's a vacuum. Now, why is this outside the realm of reality? The math tells you one thing, but let's look at one other very important factor here. If I now write between 1 and 3, I find out something interesting. P1 plus gamma Z1 plus rho Z1 squared over 2 is equal to P3 plus gamma Z3 plus rho Z3 squared over 2. From continuity, these are the same diameters. Therefore, the velocities should be the same. Now, this is a very important point here. These velocities are the same. Elevations are the same. So therefore, P1 has to be equal to P3, right? And P3 was 0. So here's the problem. How can this pressure be 0 and this pressure be 0 and the water flow from left to right? So what I'm going to do is I'm going to leave you with that thought, and we'll resolve that thought in chapter 8. So essentially, there's a hole in Bernoulli's equation, and we'll talk about that next.